Guys, welcome back to our channel, The Mysterious Files, where the shadows of history come alive. Here, we delve into the eerie, the unexplained, and the forgotten tales that time left behind. Get ready to uncover the mysteries that lurk in the corners of our past and join us on a journey into the unknown. Do you recall the blockbuster film by Christopher Nolan from 2014, Interstellar? The movie showcased space-related concepts like wormholes, black holes, and alien planets in a way that was scientifically accurate. But perhaps the most mind-blowing moment came at the film's climax, when the protagonist, Cooper, plunges into a black hole. In the film, this black hole was called Gargantua. As Cooper enters the black hole with his spacecraft, everything around him is engulfed in darkness. But as he descends further, he begins to notice grain-like particles that collide with his spacecraft, leaving scratches. There are flashes of light, sparks fly, and eventually, his spacecraft catches fire. Forced to eject, he continues to fall deeper into the black hole, only to find himself suddenly in a five-dimensional space tesseract. It's a bewildering scene where he communicates with his past self through gravity. But did you ever wonder if such a thing could actually happen? Could such phenomena really exist inside a black hole? What might we see if we were to fall into one? Let's dive into these questions in today's video. Black holes were largely a mystery until the 20th century. They're regions in space where gravity is so intense that even light can't escape. From the outside, we can't discern what's inside a black hole. Black holes are the universe's dark centers of gravity, swallowing everything in their path. Let's begin at the beginning, friends. The history of black holes isn't long. Just 100 years ago, they were completely unknown. Their discovery is closely tied to Einstein's theory of relativity, which is divided into two parts: the special theory of relativity and the general theory of relativity. Einstein's special theory of relativity, published in 1905, tells us how speed affects time. If you were aboard a spaceship traveling at extremely high speeds, time would slow down for you relative to those on Earth. But here's the key: you wouldn't notice time slowing down. To you, time would seem to pass as it normally does. However, once you return to Earth, you'd find that time had passed differently for you. This is known as kinematic time dilation. But it's not just speed. Gravity, too, can cause time to dilate, as Einstein demonstrated in his general theory of relativity, developed in 1915. The stronger the gravitational force you experience, the more time will slow down for you. This phenomenon, known as gravitational time dilation, was depicted brilliantly in Interstellar. When Cooper and his crew land on the Aqua planet, 1 hour there equals 7 years on Earth. Why? Because the planet was located near the Gargantua black hole, and the immense gravitational pull of the black hole affected the flow of time. To help us visualize this, Einstein asked us to imagine a fabric of space-time, like a mesh on which all celestial objects rest. The mass of these objects causes the mesh to bend, and the greater the mass, the more the fabric bends. This bending not only attracts physical objects, but also affects time, and even other forms of energy like sound, heat, and light. Gravity impacts nearly everything in the universe. This was another conclusion of Einstein's work. Friends, that there could be objects in the universe with such an intense gravitational force that they absorb light completely. If such objects exist, they would appear completely black to us, invisible to the naked eye, because not even light could escape their grasp. And this, friends, is what we know as black holes. However, when Einstein presented his theory of general relativity, black holes were merely theoretical. Though he knew gravity could influence light and that objects capable of absorbing light were theoretically possible, he didn't believe actual black holes existed. To him, the concept seemed too strange, almost like the existence of infinity possible in theory, but not likely in reality. It's worth noting that during Einstein's lifetime, the term black hole hadn't even been coined yet. Here's an intriguing fact. A crucial point in Einstein's theory is that the speed of light limits gravity's influence. For example, if the sun were to suddenly disappear, we on Earth wouldn't know for 8 minutes because that's how long it takes for sunlight to reach us. Similarly, the gravitational impact of the sun's disappearance would also be felt only after 8 minutes. Isn't that fascinating? Following Einstein's work, many scientists tackled the theory of general relativity, solving complex equations to prove that black holes might actually exist. By the 1960s, researchers had largely agreed that black holes weren't just theoretical, they could be real, observable phenomena in space. The term black hole was first used in a 1964 magazine, but it wasn't until physicist John Wheeler popularized it in 1967 that it became widely known. But what exactly is a black hole? Despite the term's sensational sound, it's somewhat misleading. A black hole isn't a hole in space, it's formed by the remnants of a star. Stars, including our Sun, undergo continuous nuclear fusion reactions at their cores, producing heat and light. This heat generates an outward force, while gravity pulls inward, keeping the star intact. But these reactions require fuel, like hydrogen or helium, and eventually that fuel runs out. When it does, the outward force ceases, and the star collapses under its own gravity. What happens next depends on the star's mass. Let's explore the life cycle of a star. If the star has a smaller or average mass, it becomes a red giant, which may then transform into a planetary nebula or a white dwarf. But if the star is massive, it cools down into a red supergiant and eventually explodes in a supernova, leaving behind a tiny core. If the core is small, it becomes a neutron star. But if it's larger, it becomes a black hole. Essentially, when a massive star collapses due to its own gravity, its mass condenses into a small volume, creating a black hole. Just how small does this volume become? Imagine a star as big as our Sun turning into a black hole with a diameter of only 50 chem. Can you even picture such compression? Interestingly, though, our Sun won't become a black hole. This was proven by the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who established the Chandrasekhar limit, stating that a white dwarf can have a maximum mass of 1.4 times our Sun's mass. Beyond this, it would either become a neutron star or a black hole. But since our Sun is below this limit, it won't evolve into a black hole. Let's delve into the types of black holes. There are primarily 3 or 4 types. The most common are stellar black holes, which are formed by stars. It's estimated that our Milky Way galaxy alone contains between 10 million and 1 billion such black holes. Then, there are primordial black holes, which are believed to be as small as an atom but as massive as a mountain. These are still hypothetical, and we don't know much about them. The third type is supermassive black holes. These are gigantic, with masses greater than 1 million suns combined, fitting into a space about the size of our solar system. It's believed that a supermassive black hole exists at the center of every major galaxy, including our own Milky Way, where the black hole is called Sagittarius A. The black hole named Gargantua in Interstellar is depicted as a supermassive black hole. Some scientists speculate that there may be a fourth type of black hole, intermediate black holes, which would fall between stellar and supermassive black holes in size. However, no evidence of their existence has been found yet. When you think of black holes, you might imagine them as massive, dark spheres pulling everything around them into oblivion. But they're not exactly like that. The black holes depicted in Interstellar and in the first-ever photograph of a black hole taken in 2019 reveal a different image. One striking feature is the orange ring encircling the black hole, known as the accretion disk. This disk forms as the black hole's immense gravity pulls in gas and debris, which then orbit the black hole at incredible speeds, heating up so much that they glow and emit X-rays. Interstellar accurately portrayed this disk, though in reality, it wouldn't be orange since human eyes can't see X-rays. We represent them with visible colors. The real color of the disk would be closer to blue. Interestingly, in the first real image of a black hole, you'll notice that one side of the disk is brighter than the other. This is due to the Doppler beaming effect, where the particles moving toward us appear brighter, and those moving away appear dimmer. Another fascinating detail from the movie is the optical illusion created by the accretion disk. It seems to cover both the top and bottom of the black hole due to gravity bending light. If you were to look at the black hole from above, it would appear as a regular, round disk. But from the side, gravity distorts the light, creating this unique visual effect. As you approach a black hole, you'd see a final circle of light known as the photon sphere. Here, gravity is so strong that light orbits the black hole, meaning that theoretically, you could see the back of your own head if you were in this region. Beyond this lies the event horizon, the boundary of the black hole where gravity becomes so. Thank you for watching The Mysterious Files. If you enjoyed unraveling these dark and mysterious stories with us, don't forget to like, subscribe, and hit the bell icon to stay updated with our latest explorations into the unknown. Share your thoughts in the comments below, and let us know which mysteries you'd like us to explore next. Until next time, keep your curiosity alive and your mind open because the past is never truly dead. Let me know if you'd like any adjustments.